to describe the radioactivity instead of Curie's because it's a bigger number and it scares people more. And they're not about truth, they're about scaring.
What about Ronkin? How much do you know about that?
Okay, so Roentgen has to do with energy absorbed by a target.
Okay.
And this has to do with the number of decays. So the Roentgen would depend upon how many decay products, say betas or gammas, interacted with you or an object and how much energy they carried.
Okay.
Andrew, are you asking to Chernobyl?
Well, I've read about it in several other places. I thought it was just terminology of the Russians or whatever, but I guess it's actually a thing.
Yeah, so the Roentgen is a measurable quantity, and it gives you a measure of how much radiation you're exposed to.
Okay.
Now, when you ask how much radiation did I absorb, that's a much more difficult calculation, and it can be related to the Roentgen, but and we have another unit for it called the rad.
Okay.
But things are a little more difficult to make the comparison. So we'll talk about that a little bit when we talk about nuclear power and such. All right. So if I go back to copper 64, what is its lambda? Can you calculate that for me? And calculate it for me, well, just calculate lambda.
Would the equation look like 0.38 is equal to half, or like its half-life? Is that how you would say it?
Yeah, so it's a log 2 divided by the half-life, but change the hours to seconds.
Oh yeah, that's how I failed. Okay.
So why it's log 2 and like not log half? I mean, it's decaying, right? It's
Yeah.
not increasing. So shouldn't we be using log half instead?
The logarithm of 1/2 is log 2.
Oh yeah. Just different sign, yeah.
And the
Is
minus.
it?
Yeah, go ahead.
Yeah, sorry, go ahead.
No, I was going to jump off some slightly different thing. What was your question or comment?
No, I was just asking, is it like almost 200?
Well, dividing by a pretty big number, aren't you?
Yeah.
Divided by something like 40,000.
You're divided by like 45,000 seconds.
So lambda is going to be log 2 over the half-life.
It's like 1.5, 10 to the negative 5, I guess. So.
Okay, is that what the rest of you got?
Would you say ah?
1.5 10 to the 10 to the negative 5. So
Per second.
yeah, second per second. Yeah.
Yes, sir.
All right. So let's say you've got 64 grams of copper 64. What's its activity?
How many grams?
64.
Would that just be 64 times its half-life? Or I mean, the
Avogadro's.
No. You gotta have
Uh,
the number of atoms.
yeah. It's
Oh, it'd just be Avogadro's number.
yeah, it's like 9.1 10 to the 18, I guess.
Would you get all of it? What'd you say?
9.1 to the power of 10 to the 18th.
Okay, so how many curies is that?
Could you go back to the other slide?
Yeah.
Oh, yeah.
It's in it's in the front, I guess. It's like next to it, not before it.
There we go.
Oh, cool.
So right here's the activity, and then the activity without the minus sign is right here.
Would it be 2.45 times 10 to the 8th?
Curies? Is that what
Curies?
we're talking about, Andrew?
So what was your lambda? What was your decay constant?
9.1 times 10 to the 18th. And I
Yeah,
divide
I get the same answer.
Okay, so that's lambda n. It's 9.1 times 10 to the 18.
Yes, sir.
And you divided that by 3.7 times 10 to the 10.
Yes.
Yeah.
And I got 2.45 times 10 to the 8th.
Wait, what was
Hey,
it? Lambda?
yeah. 1.5 times 10 to the minus 5.
I got 2.45 times 10 to the 8th. That's what I got. When I divided.
Is your lambda?
Curies.
Yes.
Yeah, this is what I got too.
So lambda, I think everybody got 1.5 times 10 to the minus 5 per second.
Interesting.
And lambda n is then 9.1 times 10 to the 18 per second,
Yes.
or becquerels, and then 3.7 times 10 to the 10. Now, 64 grams, how much does that weigh?
64 grams.
64 grams.
Yeah, well, let's see. That's mass. Weight would be either newtons or pounds.
No.
454 grams in a pound. About 1.5 ounces.
Could be.
And density of copper is what, about 6 or 8 grams per cubic centimeter. So if you've got 64, let's say it's 8 grams per cubic centimeter. That means you've got 8 cubic centimeters, right?
Yes.
And the cross section of your pin is probably about a square centimeter. So 8 centimeters long would be the volume of copper that you've got. Okay, a source that's emitting radiation, which copper is, that has an activity of 2.4 times 10 to the 8 curies will kill you. As a matter of fact, you won't live the night.
How many grams did you say?
64 grams.
Wow.
But you don't often see sources like that. At Oak Ridge, they had a source that we could use. It was 800 curies of cobalt-60. And it did kill a fellow who accidentally got exposed to it for a couple of seconds.
At Oak Ridge?
Yeah, they do have accidents. It was outside of the lab, though. It was another group that was using it. So it doesn't take a lot of material to make it very radioactive. And the shorter the half-life, the higher the activity. Does that make sense?
Yes.
So if you got the same number of atoms and you cut the half-life in half, that doubles the lambda. And lambda n is your activity. So if you make the half-life shorter, the activity gets proportionately higher. So there's always this question of what's a safer radioactive material? One with a long half-life or one with a short half-life? And the question is how much of it do you have? Because it's really the total activity of the source. So there are a number of things that people ask questions that seem like they're simple and straightforward, but you'll realize that mathematically they have a much more challenging answer. You've got to give a bunch of ifs that people don't like to hear. All right. Well, if I've got something that's radioactive, what can I do with it? One thing that people figured out quite quickly is that you could figure out the age of something. Living organisms take in carbon dioxide. A certain known fraction of the carbon in the atmosphere is carbon-14. It has almost a 6,000 year half-life. And that means when that organism dies, it quits taking in carbon, and all its carbon-14 is going to decay away over time. And so if you can get the material, find out how much carbon it has, and then find out how much carbon-14 is there, then you can work backwards and figure out how long ago that object was living. So there's a famous example of this. It's called the Shroud of Turin. Do you know what that is?
I do not.
I don't.
Okay, a shroud. Do you know what a shroud is? Historically, when you died and you were buried, they had a cloth that they laid down and then put the body on top of it, and the cloth was long enough that they folded it back over the body. So this one particular cloth had been captured by the Knights Templar and given to the Turin, the cathedral at Turin in Italy, or France, I guess it was. And it was supposedly the burial cloth of Christ. And There were a lot of stories with that, but that cloth was on display at Turin for decades, well, for centuries after they got it. And the question came up, say 2 centuries ago, is, well, how do you know this is it? And the answer is, well, that's what they told us it was. But with the invention of photography, somebody decided to take a picture of the shroud because it has this image on it. It has this something that's there. When they took a picture, they realized that the Shroud of Turin was like a photographic negative. And when they looked at the photographic negative of the picture they took, it gave them a positive of the shroud, and it looked like the shape of a human being. So this elevated it quite a lot, and people would come to see it. And back in the 1970s, a group of scientists got permission to inspect it and do some work.
Carbon date it.
Well, they weren't allowed to carbon date it. They were only allowed to look at it with instruments. And so there was some evidence of paint pigment that made some people think that this was not a real object. And the Knights Templar brought that to the church in about 1520 or something. And apparently there was a story that 2 people were burned at the stake for having created it, but they didn't do anything to the object. So we wondered if that was just another story. All right, so about 20 years ago, they agreed to let the shroud be carbon dated. And a good friend of mine in Switzerland was one of the labs that got to do it. He said they sent 3 samples of cloth to try to make you be objective. He said, but it was obvious which one was the old piece of cloth. But he said, we have nothing to win or lose by whether it's old or young. So, and a group in Arizona also did it, and they both came out that the cloth was from materials that were growing about 1520. So,
all right.
Yeah, so apparently they did burn the guys at the stake for good reason. Anyway, they still show it. There's still some controversy, but I think that it's that there's some controversy of how they created that image. The guy from Chicago claimed that it was just painted on, but there's evidence that it may not have been, and it may have been something else. Maybe body oil from the shroud touching someone aged and gave that coloration to the cloth. But it was being able to carbon date it that allowed them to do this, and using the half-life. There's another problem in your book that's rather interesting. It's how to determine the age of the Earth. So the Earth was created in the aftermath of a supernova of a star that burned out. And this is where you get all your heavy elements produced, in particular uranium. There are 3 isotopes of uranium, 232, 235, and 238, that all have different half-lives, all of them fairly long. But if you assume that all the uranium that was created in the supernova, that there were equal numbers of isotopes, when you look at them now, you could say, all right, if I look at how much uranium we get whenever we take some out, we can work backwards on the 3 half-lives and get to some point where the number of uranium atoms of each isotope is the same. And when you do that, you get an age of the Earth about what we expect for other reasons, about 4.5 billion years.
What are other reasons that they would suspect?
Well, they have some rocks that they recognize as something that came from the interior of the Earth, so it was probably a chemical mixture similar to that, and they can date those rocks to about 4.25 billion years. And so the uranium gives you an age when the supernova was finished. So the Earth took a while to create from that rubble. So it poses an interesting thing. And there are other combinations of radioactive elements that allow you to try to get the date objects and stones. So there are other radioactive decay mechanisms that can be used also for dating the Earth and dating other materials. So understanding just this mathematics from a living point of view, an investing point of view, looking at the spread of virus point of view, all of these involve radioactive exponential processes. And knowing something about the decay rates from that is an important idea that you need to come away with.
Isn't the for like viruses or like just pandemics, like the R naught value, that exponential value, isn't that what it's called?
Yeah, it's in those cases the decay rate. Hate to refer to that as population, but that's what happens. It has to do with how people interact. The distancing idea is a way to cut down interactions, which changes the decay rate. Yeah, so anyway, all right. So we spent a little bit more time on radioactive decay than I meant to, but that gives everybody else we're taking comps this afternoon a chance to catch up, and gave us time to just explore a little bit more about radioactive decay. So we'll pick up with some of the problems I gave you, assigned to you, and shell structure next time. All right, guys.
Dr. P, do you think we'll have class on Friday since they have the oral part of the comp?
Because all but one of them will be